But you are innocent.
Semester. Yeah. We were
online.
Yeah.
Yeah, I feel like it's like
Hey guys, how's it going?
How's your break?
Oh, it was good. Caught up on work, relaxed a little bit, and kind of mostly just stayed in. How about yours?
Not mine though.
Yeah, I know, right? I could use another week for sure.
Yeah.
You guys, the teacher got a haircut. Make sure you acknowledge it so you don't feel self-conscious.
You already acknowledged it today. I'm
I did.
good.
No, I did it earlier today. Yeah. Yeah. I noticed it was like 25. It was really low. But it's fun, so. Just keep it, I mean, I recommend that. But I think the plus that will apply to that. So, it isn't passive. But, yeah. Oh, why would you do it? That. And I'll take what? I hope she does that. Special thanks to Dr. Hope Points. She was a part of it. John. Bill. Are these really? That's probably why my 2018 final was so good. She's a great teacher. That's great.
All right, it's 4 o'clock, so let's go and get started. Good afternoon, everyone. Welcome back from the spring break. How's everyone doing? Wish spring break was longer. I know, me too. Feels like it's just long enough just to get you into the relaxation mode, and then all of a sudden it's over and you have to come back to work. So, you know, but now we're back. So the show must go on, and so we're getting ready for the end of this semester. Okay, so the plan for today is we're going to continue with our lecture notes that we started right before spring break. And so that is on impedance and vascular networks. Okay, and so we're going to continue on with that. The only assignment that I have for you guys out right now is the midterm project. And so just a reminder that it's due next Friday. I've already seen a few of you guys. And so some of you guys stopped by office hours yesterday. Some of you have talked to separately. And so it looks like your projects are coming along well. And so, you know, make sure you're working on that. And if you have any questions with the image data or with, you know, producing the model, please let me know. Okay. And if you haven't checked it yet, I did finally grade your some vascular tutorials over the spring break. So I apologize for the long delay for that. And for some of you, I left some comments to give you some feedback based on your models. Okay. And so hopefully, you know, you can incorporate those feedbacks into your midterm projects so that your models will be a little bit smoother. Okay. All right, and so that's it for my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and get started then. And so we kind of left off at not the most ideal location. So let me go ahead and just do a bit of recap. Okay. And so we're talking about impedance and vascular networks. Okay. let's talk about what impedance means first, because that's kind of central to this whole this whole chapter. So when I talk about impedance, is really just kind of an extended version, or more, I should say, more sophisticated version of what we understand as resistance. Okay. Right. And so we talked about resistance quite a bit in this class already. And so we talked about them in lump parameter models, or LPMs. We talked about that even before that with the Windcastle models. And so it's this idea that as blood flows through a vessel, or as a fluid flows through any pipe, there's going to be some viscous friction or some viscous losses that the fluid incurs. Okay. And so to sum it up in a word, so impedance basically represents how any flowing fluid inside a pipe will experience some resistance to that flow. Okay. And the primary cause of this that we talked about before in terms of resistance was basically viscous friction. Right. So anytime you have a viscous fluid, or fluid with any kind of viscosity, and you flow it past a surface, there's always going to be some viscous shear stresses that result, and that's going to impede the flow, or it's going to hold it back. Okay. The idea of impedance kind of takes this one step further. So in addition to viscous friction, which is going to play a role here, we also have things like the unsteadiness of the flow. We have things, or specifically for blood flow, we have effects due to the deformable walls. Okay. And we also have the effects of pressure. Okay. And lumped into that, I'll throw in inertia as well, because they kind of play the same kind of role. Okay. And so in addition to viscous friction, there are lots of different factors that can impede the forward progress of a flowing fluid inside a pipe. Okay. And so this idea of impedance is going to kind of encapsulate all of these factors. And so, from this chapter, we'll be able to get a kind of a more complete view of, why your heart kind of has to work so hard to pump the blood, because it has to overcome a lot more than just viscous friction. And so to get to that point, our starting point was our 1D equation of blood flow. Right. If you remember, before the break, what we did was we took our Navier-Stokes equations and we averaged them, or we integrated them across the vessel cross sections, and we obtained our 1D equations from that. Okay. And so that was our starting point. But we weren't able to work directly with the 1D equations, because remember, they were nonlinear equations. And so our first step was we linearized the equations. And all linearization basically aims to do is to take all the nonlinear terms and make them linear, either through, sometimes just straight up eliminating those terms, or by approximating them around a reference point. Okay? And the result of that was the following. And so we first had our continuity equation. Right? So this is the result of conservation of mass, which actually did not change at all, because our conservation of mass equation was already linear. Okay. And then we had our linearized version of our momentum equation. And so our momentum equation looked like the following. Okay. So those are the two equations that we were working, and we were kind of in the middle of massaging these or working with them in order to get them to a point where we can get our impedance equations. Okay? Because ultimately what we want, and this is kind of jumping ahead a little bit or looking at the location of the treasure before we actually go there, is we hope to take these equations and turn them into what's called the wave equations. Okay? Because another consequence of studying impedance is that we're also going to be able to get more information, or at least get equations for the wave propagation and wave reflection phenomenon that we've been talking about a lot in this class. Okay? So wave propagation, wave reflection, we've talked about it quite a bit in this class, and I think we all have a good qualitative understanding of what that means, right? So every time the heart pumps, it sends a pressure pulse down your cardiovascular tree, and eventually that pressure pulse is going to reflect at certain points, right? That's what wave propagation, wave reflection means, and so we've talked about that kind of in theory, but we haven't actually put any numbers to it or any kind of equation, and so that's kind of another goal that we're going to see here as well, and that idea is very closely linked to this idea of impedance. Okay? So that's why we kind of studied them both at the same time. Okay? And so that's kind of our goals for this section. And so, unfortunately, this is going to be another section where we're going to be doing a lot of heavy math. We're not going to be doing anything sacrilegious this time. But it is very easy to kind of get lost in the details. And so before we get started with these kind of things, I really want to lay out what are our goals here. And so our goals for this are to have a better understanding of what impedance is. And so, we're going to see that come out of our equations. And we're also going to need another goal of ours is to get equations that can better describe the wave propagation phenomenon. Okay? So two ambitious goals that don't seem like they're related, but you'll see that, we're going to end up in a place where, we'll have a better understanding of both of those. Okay. All right. Any questions on this? All right, so that was just kind of a recap from before break. So let's go ahead and continue on with the details. Okay? All right. So the first step in this derivation is to kind of combine these equations because we kind of have three unknowns here. So we have the flow rate, we have the cross-sectional area, and we have the pressure. Okay. And so our first step here is to kind of make a substitution that replaces the area with pressure. Okay. So that's kind of our goal. And so we have one term here that has the area still, and that's the conservation of mass equation. And so we want to do something about that term so that we can kind of solve these two equations together for flow and pressure. Okay. And so to aid with that, we're going to define a new variable. Or I should say it's a new constant, and so it's not a variable. And so it's we'll call it C0 squared. And this is going to be equal to A naught divided by rho, partial P, partial A, right? For this C naught squared here, this is defined as the wave speed. And so anytime you're talking about the wave equation, anytime you're talking about a wave of some kind traveling in a medium, right? So think about the ocean waves that travel along the ocean. They always travel at a fixed speed, and that speed is always determined based on whatever physical properties of the medium that you have. Okay. And so for blood vessels, our medium here is going to be the blood vessel walls. And so our speed here is going to be determined by the cross-sectional area. It's going to be determined by its density, but it's also going to be determined by the relationship between pressure and area, right? And this is kind of the key right here. Right? And so this derivative here states what the relationship is: pressure and area. Okay. And so that's a definition. And so, we're going to be working with that. But our goal is to use this definition to replace this term up here, right? And so let me go ahead and write this term out down here. Not like that. My stylus has been cursed the last couple of days. It's weird. Okay. And so the term that we want to replace here is partial A, partial T. And so, and we want to replace it with some kind of expression that includes the wave speed. The problem here is that we have a derivative with respect to T, which we don't have in the wave speed. And so what I'm going to do is I'm going to kind of do a chain rule. And so what we can say is that partial A, partial T, we can kind of split this up or kind of expand it, if you will, okay, into partial A, partial P, okay, and then partial P, partial T, right? And so what we say is that, if we take partial A, partial T, this can also depend on the pressure. So what we can say is that this is also equal to partial A, partial P, which is the rate of change of area as the pressure changes, multiplied by partial P, partial T. Okay. All right. And so this guy, is pretty convenient because we have a derivative that involves both area and pressure. And so what you should see is that these two look very similar, although they're kind of inverted. And so based on this equation up here, we can solve for partial A, partial P. And so what we can say is partial A, partial P, right? If we just kind of invert this entire expression up here and we move the terms to the other side, this is going to be equal to A naught divided by rho C naught squared, right? And so if we plug that in for partial A, partial P, then what we get is partial A, partial T is equal to A naught over rho C naught squared, partial P, partial T. Okay. Okay. And so now we have something that we can substitute in for partial A, partial T inside our conservation of mass, right? And so now we can take our conservation of mass expression and we don't need to use partial A, partial T anymore. We can use this one here that has partial P, partial T. Okay. And so we plug in for that. We plug this into conservation of mass. What we get is, we get A naught over rho C naught squared, partial P, partial T, plus the other term remains unchanged. And so this is our new conservation of mass expression. And so we've taken the base of partial A, partial T, and replaced it with one that involves the pressure derivative. Okay. All right, question. So is the wave speed related to the pulse wave velocity that we learned in lecture 5? It is, yes. And actually those two are exactly the same. Yeah, so the wave speed here is the same thing as the speed at which the pulse waves travel along the vessel walls. Yeah. So I think we went over an equation for it back in lecture 5. That was kind of an experimental formula, just kind of based on observations. This is kind of a more mathematical, physics-based formula for the wave speed. Yeah. So they look very different, but they represent the same thing. They're just kind of two different perspectives of looking at it. Okay. Any questions on this so far? Okay. All right. So this is a good start here, right? Next thing I want to highlight. So now that we have this equation right here, is we have this derivative here, which is our brand new one, right? Partial p partial t. If we look back at our equation for the momentum, you can see we also have a pressure derivative there, but it's with respect to z. Okay. And so we have one pressure derivative with respect to t, another one with respect to z. Okay. But you know, the convenient thing about this is that both in this equation and in the momentum equation, pressure only appears once. Okay. Eventually, we'd like to solve for both. And so eventually we want to solve for both pressure and flow rate, right? And we have the right amount of equations for that. We have two equations for our two unknowns, okay? It's just that, you know, and so theoretically we have, you know, we can solve for both. It's just that, you know, we need to actually go about solving it now, okay? And so usually when you come across these systems, the best way to kind of go about it is to, you know, eliminate one of the terms, right? And so use one equation to eliminate a term in the other equation. And the easiest one for that, or the easiest way to accomplish that, is to look at the terms that appear the least amount and then try to eliminate that one from the equation, right? And so based on this criteria here, you know, let's go ahead and try to eliminate pressure from both this equation and the previous one. Okay. And then what we're going to get in the end of that is we're going to have one single equation that we can solve for Q. It's going to be a differential equation, and in fact, it's going to be a partial differential equation. You know, but that's going to be a lot easier to solve. Okay. It's interesting, you know, because Q is actually the one we're not as interested in. You know, we're actually a lot more interested in the pressure in this case. It just so happens the way that these equations are kind of defined, it's easier to kind of solve for the flow first, then plug that back in and solve for the pressure. Okay, and so let's go ahead and do that now. And so you know, if we look back at these equations, we have the one that I boxed here. We have the time derivative of pressure. But up here, what we have is a spatial derivative of pressure, right? And so we have unmatching derivatives. And so we need to make sure those derivatives match. Okay. And so in order to do that, we have to form the cross derivatives. Okay. I think it's called mixed derivatives or something like that. I always call them cross, but you know, same thing. Okay. And so basically what we want to obtain, is we want to obtain this derivative in both equations, right? Not x, I'm sorry. So this should be z. Right, so we want partial squared p, partial z, partial t. Okay. And so to obtain that, we're going to take this equation here, and we're going to take the derivative with respect to z. because we already have a time derivative in this equation. And so if we take a derivative with respect to z, that's going to form our cross derivative. Okay, so let me go ahead and do that. And so let me start with conservation of mass. Let me just write mass. Yeah.
By mixed derivative, you just mean that have two differences, or
Yeah. So we're taking it's a double derivative, but the first derivative is in z and the second derivative is in time. Yeah. You hardly ever see this, and so I think most people, I think with mixed derivatives, I think people ask about this when they first learn about partial derivatives, and then they just forget that it ever exists, because it just never happens in most formulas. You look at things like the heat equation, Navier-Stokes, structural mechanics equations. There is no mixed derivatives, and in fact, it is very rare. The only time that you really see it is in applications like this, as kind of like a mathematical trick to kind of help you solve for certain things, but it doesn't show up all that often in practice. All right, so for the mass equation, we're going to take partial z. And so if we do that, we get A naught over rho C naught squared. It's partial squared P, partial Z, partial T, plus, we have to take the Z derivative of the second term 2. And so that's going to be partial squared Q, partial Z squared. And that's going to be equal to 0. Okay. All right. Next, we have our momentum equation. Okay. And for the momentum equation, we already have a derivative with respect to z here. And so in order to form the mixed derivative, we have to take a time derivative. Okay. Okay. So we're going to take partial t of the momentum equation. And so if we do that, we get partial squared q partial t squared plus A naught over rho partial squared P partial Z partial T plus 8 pi mu divided by A naught, and then the first order derivative with respect to time. So partial Q partial T, and that's equal to 0. Okay. Okay. And so I've taken basically our two linearized 1D equations so far and just taken partial derivatives so that these two match. Okay. And so if you look at our pressure derivatives now, look at this person and this person here. Okay. They're the same. And so now we can basically algebraically eliminate this from the equation and get a single equation for Q. All right. Any questions on this? Okay. All right, so let's go ahead and solve this then. And so we're just about there. And so in order to solve this, we're going to need to take our mass equation. We're going to need to multiply this by C naught squared, right? Just to make sure that the front coefficients match. And then after we do that, we're going to subtract these two equations. Okay? Okay. And so that's going to eliminate those two terms. Okay. And so if we do that, and I'll skip over a little bit of the algebra, although it's not too much. Okay. Then what we get is the following equation. So we have partial squared q partial t squared is equal to C naught squared partial squared q partial z squared. Okay, so that came from the first equation, and it's on the other side because we subtracted them. Okay, and then we subtract 8 pi nu divided by A naught partial q partial t. And so what we have here is an equation. It's a rather complicated equation, but we've eliminated pressure, and now we have a single PDE that we can use to solve for Q. Okay. Has anyone here taken 438 or learned how to solve PDEs before? All right, so you're gonna get a crash course in it today. One thing before we start though is that remember, what we said was we hope to obtain some kind of wave equation, because what we expect is that the pressure behaves like a wave, and by by conjunction, the flow is going to behave like a wave too. The form of this equation is very interesting, because this form exactly matches up the form of the classical wave equation. Okay. And so the classical wave equation is basically you have a second order time derivative on one side of the equal sign, then on the other side you have a second order space derivative, and then and you can have some extra terms too. But basically the main part of the wave equation is these two terms right here. Okay. And so you have a second order space derivative, second order time derivative, and then you might have some extra stuff on the other side. Then that's your wave equation. This extra stuff, this extra stuff here, this is what's known as damping. And so this is kind of extracurricular to this class, but in case you do end up taking a PDE class, you'll probably be solving this equation to some capacity, because it's one of the classic PDEs. Okay? And so you'll probably start with the undamped version, which is the first two terms that I circled, and then you might move on to the damped version, which has this one. Okay. And so let's go ahead and solve this. And so solving partial differential equations is not a it's not a trivial thing. It takes there's a reason why it's usually a graduate level course. And so we're not going to go through the entire pantheon of PDE solving methods, because that's literally two entire courses that we have here. So we have 438, 538, and if you're a grad student, you'll take those, and some of the grad students here might already be taking those. Okay, but for this problem, we're going to take kind of a simple approach, or one of the simplest approaches, in that we're going to assume that our solution is separable. Okay. Okay. And so what does that mean? And so, whenever you have a PDE, a partial differential equation, that means your quantity of interest, or the variable that you're solving for, depends on more than one variable, right? Okay. And so in our case, we have two variables that we're solving for, or two dependencies, and our dependencies are Z and T, right? And so in our case, flow depends on Z, where remember Z is the centerline coordinate. And T, of course, stands for time. Okay. And so that's what our flow depends on. So it's going to depend on both of those variables at the same time. Okay. And so our solution here is some function that involves both Z and T to some degree. And so if you think about the space of functions that contain both Z and T, it's infinitely many. Okay? But for separable situations, what we assume is that they look like the following. And so we have a certain function, and so we'll call this Q1 of Z. Okay, it's a function of just Z, and so there's no time dependence here. Okay? This is going to be multiplied by another function, which depends on time. And so in other words, we can take the two dependencies, we can take the two variables that this depends on, and separate them into different functions that are multiplied by each other, okay? And so that's what it means to be separable. And so we can basically separate the two dependencies into separate functions. Okay. Because it could be a lot more intertwined. And so, you could have a function that incorporates both z and t, and you can't kind of pull them apart like this. And so, it's a big assumption, but a lot of classical PAEs kind of fall into this category. Okay. We're going to make one additional assumption here, just because we kind of have a little bit of physical knowledge about our flow, right? We know that the time dependence in cardiovascular flow is cyclic, right? And so the heart beats with a regular frequency, and we know that the waveforms, both the pressure and the flow, are going to go up and down, okay? And so we know that this function here is going to be some kind of cyclic function or periodic function. Right? And that's just based, purely on just knowledge of our physical system. Okay. And so we can do a little bit better here. And so we can do a little better than just saying this is some generic function of t. What we can assume now is that this is some sinusoidal function of t. Okay. And so instead of q2 of t, what we can use instead is we can say this is equal to e to the I omega t. Okay. Where e to the I omega t is equal to cosine omega t plus I sine omega t. Okay. And this formula right here, this is a very classical Euler's law. And so you'll see Euler's law used a lot in these kinds of situations because periodic functions happen a lot, and sine and cosine are the two kind of classical periodic functions. But if you can't decide between sine and cosine, or more like you don't have a reason to decide between sine and cosine, you can use e to the I omega t instead. Okay, so it's a little bit strange notation to think of e to the some kind of exponential function as being periodic, but that's just kind of the standard way to think of these. It actually makes the math a lot easier, believe it or not, because we're going to be taking derivatives of this quantity, and taking derivatives of an exponential function is a lot easier than a sinusoidal function in general. Okay, so that was a lot of kind of mathematical reasoning and kind of assumptions that we made. So let me check in here. So are there any questions on anything that we've done so far? You guys are getting a crash course in PDEs, and so you probably didn't expect that when you signed up for this class. Okay. And so now that we have this form of the function, right, we can go ahead and plug this into our wave equation. And you'll see very quickly the power of having a separable function like this. Okay? And so the wave equation is up here. So basically everywhere we see q, we're going to plug in this expression right here. Okay. All right. So first thing we have is a second order derivative with respect to time. So we have partial squared, partial t squared of our assumed function. And so we have q1 of z e to the I omega t. Okay. Is equal to c naught squared multiplied by a second order derivative with respect to z. And so we have partial squared, partial z squared of q1 of z e to the I omega t, okay, minus our viscous term. So we have 8 pi nu divided by a naught. And we only have a first order derivative with respect to time. So partial t of q1 of z e to the I omega t. Okay. Now that we have the equation in this form, and so we've plugged in our assumed separable solution, we can go ahead and carry out the derivatives. Okay? So let's start with the first term here, and you'll see why we assume it's separable. Okay. So we have this function q1 of z, right? this Q1 of Z is only a function of Z. And so it's not a function of time at all. Okay. And so what that means is that, when we take a derivative with respect to time, this does not get affected by it. And so we can just kind of pop it out of the derivatives here. And so when we perform that first derivative, we have Q1 of Z, which is unaffected because it's not a function of time, right? And then we have the second order derivative of e to the I omega t, right? And so if we take the derivative of that, then we get the coefficient in front of t here. So we have I omega, okay? We're going to have I omega squared because we're going to take two derivatives, right? And so you take the first derivative, you have I omega that first comes out, but then you take the derivative again, then you have I omega come out again. So we have I omega squared, okay? And so after that, then we have e to the I omega t. Okay? Because the derivative of an exponential is just the exponential itself. And of course, we can simplify this. And so I here is our imaginary number, right? And so we know that I, the imaginary number, is equal to square root of -1, right? And so if we take I squared, this is just going to be -1. Okay. And so with that in mind, then the I is going to cancel out here. And what we get from this first term is going to be a minus Q1 of Z omega squared e to the I omega t. Okay. And so assuming that our function is separable helps us out a lot here because we don't have any cross derivatives. And so we can kind of apply the derivatives kind of one by one to each part of our solution. All right, so let's go ahead and do that to the other terms now. And so let's go ahead and apply the space derivative. And so the space derivative, we have C naught squared, okay? Then we have a derivative here with respect to Z. And so the only function of Z here is Q1. And so we're gonna have D squared, Q1, DZ squared, okay? And then e to the I omega t is not a function of Z. And so that just kind of pops out just like that. And then finally, we're going to apply the same thing to this last term here. And so we have a minus 8 pi nu divided by a naught. When we take the time derivative here, we're going to have an I omega that pops out. Okay. And then everything else is going to stay the same. So we have Q1 of Z e to the I omega t. Okay. So we're getting warmer here. And so we're getting to a point where we're going to be able to solve this this equation. Before we do that, are there any questions on how we got to this point? Okay. All right. So now that we've carried out the derivatives, our next step here is to simplify. And so we have something that we can do kind of right away to kind of simplify this greatly, right? And so if we look at the three terms in our expression here, we have an e to the I omega t here, e to the I omega t here, and then e to the I omega t there, right? And so if we have all three terms that have the same part or the same same expression, we can just go ahead and cancel all of those out. Cancel. All right, so that's the first thing we can do. Next, we see that we have two terms here that have Q1 of Z. Okay, and so that's the last term right here, and also this very first one that we computed as well. Right, and so both of those have some kind of Q1 of Z. So the last term here has a derivative of that, but we'll kind of leave that one alone. And so let's go ahead and combine those two. Okay, and so what we get from that is, on one side of the equation, we have a C naught squared d squared Q1 dz squared, right? And this is going to be equal to, and so we're going to move this 8 pi nu over a naught. We're going to move it to the other side. And so we have an 8 pi nu divided by a naught minus omega squared times Q1 of Z. And I forgot an I omega here, and so there should be an I omega on that first term. Sorry. So I omega times that. Okay. I'm gonna go ahead and divide both sides by C naught squared, just so we can isolate the second order derivative. Right, and so we have d squared Q1 divided by dz squared is equal to 1 divided by C naught squared times I omega 8 pi nu divided by a naught minus omega squared Q1 of Z. And so at this point, we're basically done. And so if I make kind of one step here, it'll make things pretty nice. Okay. And so let's look at this entire coefficient right here. So we have things like the wave speed, we have things like the reference area, the viscosity, pi, omega, omega squared, right? The nice thing about all of these quantities here that I've kind of indicated in blue is that all of them are constants. In other words, they do not depend on Z, right? Because the only thing that depends on Z here are the Q functions, okay? And so since all of this is a constant, let's kind of make our lives easier so we don't have to write this big expression, and let's replace this with another variable. Okay. Right. And so if we define a new constant here called lambda squared, and so we define lambda squared as 1 over C naught squared times I omega 8 pi nu divided by a naught minus omega squared. Okay. If we do that, then our equation becomes a lot simplified, right? And in fact, it becomes an ordinary differential equation. And so, this is something we can definitely solve. And so this becomes an ordinary differential equation that we can solve for Q1 of Z. Okay. It's been quite the journey to get to here, I know, but we're almost there with Q, but then once we find Q, we have to plug it back into solve for P. So I'm not going to say we're almost done, but we're at least almost there for the Q. All right. People often ask me, if people who are interested in grad school, what they should study, before they go to grad school. I tell them the same thing every single time: math. And so math is the skill that you really, really need to do in grad school, because a lot of grad school courses kind of start out at this level, and they kind of expect you to know a lot of these things. And so the better preparation you have in math, the more classes you take in math, the better prepared you're going to be. Okay? The only thing in grad course is that they usually do kind of the same thing we did, but they probably just go at 2 times speed and skip half the steps too. And so it really helps to have a lot of the math prep ahead of time. Okay, any questions on this? Okay, and so let's go ahead and solve this. And so this is a fairly easy ODE to solve. And so let me put it into a different form just to make it a bit more clear. Okay. All right, and so if I move that lambda squared over to the other side, then we have an equation that we can solve with the characteristic equation. Right? And so if you recall from 308, what you can do is you can basically form the characteristic equation. And what you can say is that you can replace this with sigma, okay, equal to 0, okay. Solve for sigma. And so sigma is equal to plus or minus lambda. Okay. Then your solution, the general solution, to this will be Q1 of Z is equal to C1 e to the sigma 1 Z plus C2 e to the sigma 2 Z. Okay. And so we plug in for sigma here, then we get Q1 of Z is equal to C1 e to the lambda Z plus C2 e to the minus lambda Z. Okay. All right. So now we finally have our expression for Q1 of Z. Okay. All right. So now that we have Q1 of Z, I mean, we don't have the full solution yet because we have to solve for C1, C2. But let's go ahead and plug this back in to solve for the pressures. Okay. Right, and the equation that we're going to plug back into is the conservation of mass equation. Okay. And so just to kind of remind you, our conservation of mass equation was A naught over rho C naught squared, partial pressure, partial T, okay. To this, we're going to add partial Q, partial Z, and this is equal to 0. And so let's go ahead and substitute in for our for P and Q here, okay? But just like we did for Q, we're going to assume that P is separable. Okay. And so P, which is a function of Z and T, is going to be equal to some function of Z multiplied by e to the I omega T. Okay. And same thing for Q. And so Q is going to be equal to Q1 of Z e to the I omega T. Okay. And so we're kind of starting at the same point here. The only difference is that now we know what this is. Right? Okay. And that Q1 of Z in that assumed solution is what we just solved for up there. So that Q1 of Z is going to be C1 e to the lambda Z plus C2 e to the minus lambda Z. Okay. All right, so let's go ahead and plug in our assumed solutions. Okay. And so first we have an A naught divided by rho C naught squared. We have partial P partial T, and so this is going to be P1 of Z times I omega times e to the I omega T, okay? Plus partial Q partial Z. So partial Q partial Z, we're going to take the Z derivative of this guy up here. And so that's going to be a C1 lambda e to the lambda T minus C2 lambda e to the minus lambda T, okay? That's going to multiply by e to the I omega T. And so let's go ahead and cancel out these terms. And so we have an e to the I omega T on both expressions there. And so those are going to cancel out, okay? And we can just solve this straight up for P, okay? And so the convenient thing is that our pressure here is going to depend on the same constants. And so, it's going to depend on both C1 and C2 from Q. It's just going to be modulated a little bit, okay? And so if we solve this expression for P1 of Z, then what we get is P1 of Z is equal to minus rho C naught squared times lambda divided by I omega A naught times a C1 e to the lambda T minus C2 e to the minus lambda T. Okay. So we took quite a journey to get here. And so, let's take a, before we move on, because the next step is to apply boundary conditions. Before we move on, let's just kind of summarize the steps that we took in order to get here, okay? And so we started out, basically with our 1D equations, right? And we kind of manipulated them a little bit so that we can get them in terms of pressure and flow, right? And so we start out by eliminating area from our equations, at least from the mass one. Right? The next thing that we did was we said, okay, now that we have these two equations, I can see that we have pressure and flow in both of these equations. Okay. Right. We have these equations up here, right? And so here we have pressure and flow, and this equation up here we have pressure and flow, right? And so we have two equations and two unknowns. And so let's go ahead and manipulate these equations so that we can solve for one of them. And it turns out, just based on how these equations are formed, it was a little bit easier to eliminate pressure first. And so that's what we did. And so we took the derivatives of both equations, right, in order to form the cross derivative, so that we can eliminate these two terms. Okay. And so after we did that, we obtained this equation, which is the classical wave equation for the flow rate. Okay. So we have partial squared Q partial T squared is equal to C naught squared partial squared Q partial Z squared minus 8 pi nu A naught partial Q partial T. Okay. So that's our damped wave equation. And so it was a partial differential equation, but at least it was only in terms of one solution. So what we said was, we can take this equation and we can actually, solve it. Okay. And then we launch into a kind of a really fast crash course of how to solve for PDEs. Okay. And so we assumed that our solution was separable. And so we assumed that the function took the following form, as in a function of Z, which we don't know yet, multiplied by a periodic function, which was our e to the I omega t. Right? We plugged that into our equation. We carried out all the derivatives, and we did a lot of algebra along the way, and we ended up with the following ordinary differential equation for Q1 of Z, which was the function of Z that was unknown earlier. Okay. And what we did from here is that, now that we have this ODE, we said that, I know how to solve ODEs. I took a class in that. And so, we went ahead and solved that. Okay. And we ended up with this function of Q, or excuse me, this function of Z. Okay. And then what we did from there, we said, okay, that's great. Now that we know Q, we can take this and solve for pressure, which is what we were actually interested in, right? And so we took this solution, we plugged this back into our mass equation, which had both pressure and flow, okay? And then we manipulated that equation in order to get this expression here for the pressure, okay? And so finally what we have here is basically this expression here. It's not the cleanest in the world. It is quite messy, but this equation right here basically describes how pressure varies down the length of a vessel okay, in cardiovascular flow. Because we have pressure as a function of Z, which is the centerline coordinate. Okay. Yeah.
Kind of lost on further back, whereas Q1 of Z, and it's all with respect to Z.
Mm-hmm.
Yeah, the bottom equation right there.
Yeah.
And then, so we took the partial of Q with respect to Z, and how did we get T in the last equation?
You mean this one? Oh, you're right. So this should be Z's. Thank you. Yeah. Yeah, you're right. Because this the function Q was respect to Z, not T's. I think just by instinct, whenever I see exponentials, I put them in time, but this should be Z's. Yeah. Yeah. Thanks for catching it. Yeah. So it's so for the complex exponentials with the Euler's law, the e to the I omega t's, those ones have t's, but when we're plugging in for q's, those exponentials should have z's. Okay. Any other questions on how we kind of got to this point here? Okay. All right. And so, we've reached this point here, which is really great. And so we've taken our really complicated PDE and we've gone ahead and solved it as far as we could. And so the next step here is to solve for these constants, C1 and C2. Okay. And to solve for the constants, we're going to use, basically the same technique that we always have whenever we experience these constants, is that we're going to apply boundary conditions. Okay. And we're in luck here because, because we have two functions basically, so we have both Q and P. We can use both because they both depend on the same constants. And so, what you're going to see is boundary conditions that kind of utilize both of these things together. Okay? And so to apply boundary conditions, we need a boundary. Okay. And so we're going to apply it to a stereotypical blood vessel. And so we have a blood vessel here, which we're going to assume is basically a tube. Okay. On the one side, we have the inlet. Okay. And so blood is going to enter the vessel from the left. And on the other side, we have the outlet. Okay. And what we're going to assume in terms of Z is that this inlet here is going to be Z is equal to 0, right? And so that's going to be the origin of our domain. and then the right side is going to be Z is equal to L. Okay. And so what we're assuming basically is that the vessel has length L. Okay. All right. And so we're going to apply conditions at both the inlet and the outlet. Because we need two boundary conditions to solve for our two constants. And so at the inlet, what we're going to assume is that we are going to assume that we know the flow rate coming in. Okay? And so mathematically that looks like this. And so we say that Q1 of 0 is equal to Q naught. Okay, where Q naught is a known quantity. And so that's the condition we're going to apply at the inlet. At the outlet, we're going to assume that the flow and pressure there are going to be connected through an impedance. Okay. And so basically what we're going to have P1 of L, right? So that's the pressure at the end of the vessel minus Q1 at L, okay? This is going to equal to 0. But modulating this is going to be some impedance times ZT, okay? And so this ZT right here, this is what's known as a terminal impedance. And so terminal impedance is a key term here. And so remember, we started this lecture off today talking about how impedance represents, kind of like a resistance to flow, right? And so for this vessel, even though I kind of drew it as just kind of a vessel by itself, in actuality, after the blood flows through this vessel, it's going to flow into other vessels as well, right? And so what the terminal impedance represents is it represents the impedance of all the vessels that are downstream of this particular one. Okay.
Excuse me, is that a T or a I for the substrate condensation?
It's a T, so it's a T for terminal. Yeah. Mm-hmm. Okay. Because when I draw vessels like this, they're not emptying the blood into some bucket, or they're not emptying out in some air, right? And so it's emptying it out into other blood vessels, right? And that's the case, everywhere in your cardiovascular system, because your cardiovascular system is a closed loop, right? And so there's never a point where your heart's gonna pump blood and it just empties out into nothingness. And so it's always gonna empty out into some other vessel, because eventually whatever blood that gets pumped out comes back to your heart. And so there's always going to be some kind of impedance or some kind of resistance to the flow that's associated with all the vessels that are downstream. Okay. Because all those vessels, they have viscous resistance, they have their pressure, they have their size, they have their wall deformation effects, and so all of that is going to cause some kind of, you can almost think of it as like a back pressure or some kind of back resistance to this blood vessel. Okay. Okay, and so that's the condition we're going to put at the outlet. And so we're at the outlet, we're basically going to assume that we know, how much impedance there is downstream of this vessel. Okay. So those are our two boundary conditions. And so now we're going to apply. Okay. And so first, let's apply the first one because that's a little bit easier to do, right? So we know that Q1 of Z, this is equal to C1 e to the lambda t, or excuse me, I did it again. So it should be C1 e to the lambda Z plus C2 e to the minus lambda Z, okay? And so if we apply this, and so we say that Q1 of 0 is equal to Q naught, okay? We plug in 0 for Z and we get C1 plus C2. Okay. Right, and so applying the first boundary condition, we simply get that C1 plus C2 is equal to Q naught. Okay. Right. Now for the second condition. And so the outlet condition is we have P1 of Z. Okay. We have P1 of Z is equal to ZT, Q1 of L, or excuse me, should be P1 of L is equal to ZT Q1 of L. Okay. Because we're applying this at the outlet. It's not at a generic location Z. Okay, so let's go ahead and plug in for those. And so first we have P1 of L. Okay, and so we're going to take our expression of P1 of Z that we have up here and just plug in Z is equal to L here. Okay. And so we do that, we get minus rho C naught squared lambda divided by I omega A naught multiplied by minus C1, or excuse me, I did a reverse here. Should be C1 e to the lambda L minus C2 e to the minus lambda L. This is equal to ZT multiplied by Q1 and L. And so we have C1 e to the lambda L plus C2 e to the minus lambda L. Okay. Right. And so here is our second condition. Okay. And so we're going to make another substitution here. And so I know I've done this 3 times or more in this class. And so I know it's getting difficult to remember all the variables. And so, we have lambdas, we have C naughts, we have A naughts, omegas. It is a lot to keep track of. But this is kind of the setup. And so, a lot of these substitutions, at least these later ones, will kind of make things make a bit more sense later on. Okay. And so I'm going to make a substitution for this term right here. Okay. And so since this is kind of a handful, we can go ahead and plug in for this. But the nice thing about this quantity here, if you look at all the variables, all of these depend only on the vessel of interest. Okay. And by vessel of interest, what I mean is the vessel that I drew up above with the single inlet and single outlet. Okay. And so this describes things like the wave speed in that vessel. It describes the density of the blood. It describes the reference area in that one. Okay. And so one way that we can interpret this is we can interpret this as the impedance of this vessel itself. Okay. And so the term that we're going to use for this is we're going to use a term called Z naught, okay, where Z naught here is what's called the characteristic impedance. Okay. And so it's different than the terminal impedance, because the terminal impedance represents the impedance of all the vessels that are downstream, all the vessels that we don't see. Z naught here represents the impedance of this particular vessel. Okay. And so if we plug that in, then what we get is minus Z naught times C1 E lambda L minus C2 E to the minus lambda L is equal to CT times C1 E to the lambda L plus C2 E to the minus lambda L. Okay. And so that kind of simplifies things a little bit for us, you know, because we aim to solve for both C1 and C2. Okay. All right. Okay, so we are out of time today, and so you know there's only just a little bit left of this derivation, I promise. And the next time we meet on Thursday, we'll actually talk about how do we actually use these results to do practical stuff. Okay. I know it was a lot of mathematical details today, and you know I usually don't like doing this. I feel like I've said that 3 or 4 times this class, but you know that's just kind of how it is with these things. But you know, hopefully it'll become more clear on Thursday. So any final questions before we wrap it up for today? Okay, all right, and so we'll stop here for today, and then Thursday we'll pick this up. We'll finish up this derivation. There's only a few more lines to go, and then we'll see how to actually use this for calculation. Okay? So thank you everyone for tuning in. Hope you guys enjoy the rest of your day, and I'll see you guys on Thursday.
Of course.
Yeah.
Earlier in class, in the beginning, you mentioned the midterm being due on April 15th.
Yeah.
Did you mean the entire midterm?
Yes. So so your model should be complete by then. And so the 8 vessels for your model should be turned in by next Friday.
My next Friday. Okay. Thank you.
Yep.
You